do this again. So, guys, today we're going to look at related rates. And I will tell you that pretty much, go back to this. Pretty much every example we're going to do the derivative. We're going to do the derivative with respect to t. And then in here is going to be whatever the equation is that we're dealing with. Guess what t stands for? Time. One of the most common rates that you guys are familiar with is 55 miles per hour. That is a rate relating miles to hours. 55 miles per hour means you're going 55 miles in exactly 1 hour. Okay? So this section on related rates, almost every problem we do is going to be a differential with respect to t. So when we look at this first example here, here's the equation. We've got y equals x squared plus 3. Guess what the very first thing you're going to do? You're going to do the derivative with respect to t. You're going to do all of them with respect to t. So what we're going to do is we're going to do the derivative of this side with respect to t, and we're going to do the derivative of this side with respect to t. Okay, great. What is the derivative of y with respect to t? dy dt. By the way, what's the derivative of x? 1, right?
Yes.
That's when you're doing the derivative with respect to x. Here I'm doing the derivative of the variable y with respect to the variable t. Those two things don't match. Now I'm just letting you know right now, if this right here had been d dy, it would have been 1.
Ah, okay.
Okay. All right, now let's do the easier one first. What is the derivative with respect to t of 3? 0. Because it's a constant. Okay, does that make sense?
Yes.
All right, now harder. Well, a little bit harder. What is the derivative of x squared? Don't say it out loud. I want you to just write down what you think it is, unless you're writing in pen. If you're writing in pen, you might not want to. What is the derivative of x squared with respect to t? Write it down. Got it? Did you write that down?
Yeah.
If you wrote that down, that's this section. It's really not much more difficult. It's all based on implicit differentiation, and that's why we did section 2.5. That's why I started with the warm-up there, just to kind of get you going in that mindset. Okay, well, let's see here. In this particular problem, what are we given? Well, we know that dx dt is
2.
So guess what I can put in here?
2. And we're also given x.
We also are given x, which is what? What are we trying to find? Oh, I think I put x equals 1 there twice. I don't know why I did that.
So if we're trying to find the way to 2, we just...
What's the answer? 4. I think it's just 4. So it's going to be 2 times 1 times 2, which is 4. Was that hard? Yes.
Is that like the chain rule? To find the...
It is like the chain rule. That is exactly what implicit differentiation is the chain rule. It's exactly what it is. I hope I hit 20. Okay, good. Let's try another one. All right, this is where it gets a little bit harder, okay? Because here, how many equations have I given you?
0.
A 0. You have no equations. And here's what the question, and it's a ridiculous question, right? It's contrived, completely contrived, but it's most of the time in math when we give you contrived questions, it's because we're trying to make it so that it's actually doable based on the math that you know. So it says a 25-foot ladder is leaning against a house. Okay, so here's our little ladder. It's 25 feet long, leaning against the house. The base of the ladder is pulled away from the house at the rate of 2 feet per second. How fast is the top of the ladder moving down the wall when the base is 7 feet from the house? Now I'm just going to stop right there. I'd like you to think about how you would even begin that. My guess is a lot of you would be like, I have no idea. Does someone have an idea, though? Yes?
Can you do something where it's like in the x direction and the y direction?
Yes. But we need an equation, right? Someplace to start. Wouldn't it be nice if there was like a right triangle or something in the picture? Oh, there is? Oh, okay. So there is kind of a right triangle here. Let's kind of make that in red. It's kind of a, now by the way, I need to forewarn you that they don't always give you a picture. A lot of times they do, but not always. And by the way, you guys would agree that this is a right triangle, correct?
Yes.
Do you guys mind if I call this X and I'll call this Y and I'll call this over here Z? You could pick different letters. Are you with me?
Yeah.
And by the way, what would be the equation I'm going to use since that's a right triangle? X squared plus Y squared equals Z squared. Okay, good. Okay, so things are looking good here. How are we doing? Okay, we're doing great. We still got 20 minutes left. Okay, so guess what we're going to do to that? Guess what we're going to do to that? We're going to do the thing. We're going to do the derivative with respect to t. Okay, so let's go ahead and do that. So, by the way, if you're taking notes, you'd be saying, okay, the first thing, and by the way, in my presentation, the video that's posted online already that I made like a month and a half ago, gives you kind of the steps, but you need an equation, right? You want to try to come up with some sort of equation. So now we're going to do the derivative of this side with respect to t, and the derivative of this side with respect to t. So that's what you always are going to do. I guess I shouldn't say always. There's always some exception. So what is the, well, we just did that one, didn't we? Did we do the derivative of x squared a second ago?
Yep.
What would be the derivative of y squared then?
2y.
2y dy dt. Z? 2z dz dt. Now, by the way, if you were looking at that and you're thinking, okay, I think you can handle it. The hardest part of these problems is just getting them going, getting them set up. Can I clean this up at all? Can I divide through by 2?
Yes, you can.
I mean, that'd get rid of the 2. I mean, you don't have to do that, but I mean, I like to make stuff easier if I can. Would you guys agree with that? Now, again, I'm just telling you that was an optional step. And you might say, Mr. Allen, that seems like it would have been a lot. Yeah, I would do that, but you don't have to. Okay. So let's see what stuff we can plug in here. Okay. So let's go back up here and let's get my highlighter. What's that?
That's the rate of the x.
That's a rate. This, in fact, let me write it up there and let's do it purple. This says away from the house. That's this guy right here, right? Ooh, I'm still on highlighter. I don't want to be on highlighter. I want to be on 10. So what's that going to be?
The x rate.
dx dt. So this is dx dt. So can you guess what I'm going to put in for dx dt?
2.
I'm going to put in a 2. Does that make sense?
Yes.
Oh, by the way, guys, obviously I've done this example before class. If you were doing this on your own, it's not quite so. It doesn't. That's the thing. I think students think that somehow math's supposed to you just get it done. When you're learning this stuff, it takes you more time, and it makes you frustrated, and you want to cry and stuff like that. But you try to persevere, and if you get stuck on something, you ask your buddy, and then your buddy might give you some insight. Yeah.
So what we're trying to find is dy dt, right?
Yes.
So
Okay, hold on. Don't jump ahead. Let me lead this, okay? You got a question?
Why did the 2 go with the x?
Okay. So here it says the rate away from the house, and it's even marked right here. So this ladder's sliding this way, right? So that's the x. And by the way, if you'd used a different letter here, it would have been like let's say you'd used the letter A. It would have been dA dt. Does that make sense? I just used x because I'm used to vertical being x and horizontal being x and vertical being. Anyways, moving on. Can I plug anything else in? What's this telling me?
that's the x. That's what we're trying
That's the x. Okay, fine. Oh, wait a minute. What's z?
25.
That's given as well, isn't it? Wow, that's so nice. Thanks. Let's do it in, I don't know. Ooh, that's probably not going to show. I'm going to do it red. Sorry, guys. So that's 25. So that's going to be 25. Okay, great. By the way, we still have 1, 2, 3 unknowns. That's not good. We'd like it to only be one unknown, right? Does anybody know what I should be putting in for dz dt? At what rate is the ladder?
It's not.
It's not. So what's the
It's zero.
It's 0.
Okay.
That's a very important observation. The ladder's length is not changing. Its rate of change is 0. And by the way, 0 times 25 is 0. So that's nice. Thank you, Dave. That's good. Now I need either y or dy dt. Man, it'd be nice if there was some theorem that told me that if I knew the hypotenuse was 25 and the leg was 7, how I could find the other side.
It's the Pythagorean theorem.
The Pythagorean theorem, right? Let's do that in this screen here. So we know that 7 squared plus y squared has to equal 25 squared. Then you guys can work that out, but let's pretend you did. It turns out to be 24. Is that okay? Can you just trust me?
I will- Yes.
25 squared, I think, is 625.
Mhm.
7 squared is 49. If you subtract 49 from 625, you get 576, and square root of that's 24. Yes?
What happened to the 2? Wouldn't that be multiplied by 7?
I haven't done anything with that.
Oh.
All I'm doing right here is I'm telling you if this is 7 and this is 25, what's this length got to be? So I'm not actually doing the differential equation right now. So that tells me I can plug 24 into there. Now I'm going to rewrite this whole equation now. Let's do it in black. The whole equation now can be rewritten as 7. Oops, that's horrible. Well, I'll fix that. 7 times 2 plus 24. That's 24. It's kind of like a y. Dy dt equals 0. Boom. And you will get, when you solve this,
Negative
dy dt is going to be negative 7 over 12 feet per second. Why is it negative?
Because it's going down.
Because it's going down. Yes.
Do we know that it's feet per second just because the
It's given to us in here that this is feet and this is per second, so the units will stay the same.
Okay.
Now, I will warn you, some questions, and I've even seen this on the AP exam, you got to be careful. Sometimes they're tricky, and they'll put something like feet per second here, and then they'll put something else in terms of inches. You need to make sure you get everything in the same units. And it doesn't matter if you make them all feet or all inches, but you need to be in the same units. Now, would you guys agree that that was a much harder problem than the previous one, right?
Yes. Yeah.
So when you do your homework this week, the first 1 or 2 are going to be like number 1, which is basically, can you just do the derivative and then plug stuff in? This one here requires much more effort and obviously some insight. Like, for example, Dagan's insight right here that was 0. That's an important insight. The other thing we could have done on this problem, just to let you know, is right from the get-go, what does x have to be? Or what does z have to be? Had to be 25. And what's the derivative of 25 squared?
0.
Okay. So it would have worked out either way. Questions on this one before I move on to our last example? Yes?
So when you're trying to plug in the numbers, when you're at the x, dx, dy.
This thing here? Yep.
Yeah, that stage.
Mm-hmm.
So like for your x, y, and z, it's just like the concrete number, right? And
Correct.
Then, like the dx.
Yep, so this was x, this was y, this is z, so that's what I put in there. So this was 25, that was 20. We had to find this one using the Pythagorean theorem.
So for the other ones, it's like the rate of
It is the rate of change, that's right. And the rate of change in this problem, they gave us that this was 2, so that's why the 2 went in there.
Mhm.
Here's what we were trying to find, so that was and by the way, when you get to this step right here, after you substitute, how many unknowns should there be?
1.
There only should be 1. And if you still have more than 1, you know you're missing something. And it's usually something that you can figure out, like using the Pythagorean theorem or something like that. Any other questions on this one? Okay. This is kind of a classic related rate problem. Classic. Okay. There's others that are like this. The one that comes to mind is baseball players running around the bases. It's the same idea. You do a Pythagorean theorem and okay. Let's look at one more. Now again, I've already done this problem and I've worked my way through it kind of methodically. If you were doing this on your own, it probably wouldn't go quite so smoothly. Agreed? Okay, last one. And I'm only just doing 3 today. Hopefully this is helpful, right?
Yeah.
Like, I don't know if you guys would have figured out the last one on your own, right? But that's what we got to try to get to. All right. A spy uses a telescope to track a rocket launched vertically from a launch pad 6 kilometers away. So I got a little picture here again. At a certain moment, the angle between the telescope and the ground is equal to pi over 3. And is changing at a rate of 0.9 radians per minute. What is the rocket's velocity at that moment? By the way, could you see how this might be actually something, like the last one's pretty contrived, right? Like, who really cares how fast the ladder's sliding down the side of the house? I mean, really, who cares? I just don't want my dad to break his legs or whatever, right? But could you see how someone might want to know that? By the way, that's what calculus is all about. That's why this is such an important section. Calculus isn't about calculus. Calculus is about solving real-world problems that involve rates of change. And that's what the derivative is. It's the instantaneous rate of change, and that's what we're trying to find here. How is this one different than the last one, though?
There's an angle.
Correct. Notice in the last one, I didn't talk about angles at all, but this one's talking about an angle. In fact, it's telling us that this angle is pi over 3. Can anyone guess what we might need to use on this problem? Sine or cosine or tangent. So this comes back to trig, which you first started learning about trig when you were in geometry, and then you learned hopefully a little bit more last year in pre-calc. And this is basic. These aren't trig. Well, yes, let's just get to it. Now, in this case, let's just kind of use our picture here first to kind of get things going. Where do you think I should put this? That pi over 3. Where the theta thing is, right? Does that make sense? So I'm going to put pi over 3 there. Okay, great. By the way, how far is the launch pad away? So this is 6. And technically, I can say that this is radians, right? We're in radians, not degrees. By the way, in this class, we almost always use radians. We're probably going to need information about the height of this thing, right? Because we're trying to find the rocket's velocity. That's going to be dy dt, wouldn't it? Again, if we think about this down here as x and this is y, does that kind of make sense?
Yeah.
Which of our trig ratios, by the way, notice we don't even care about this side in this problem. Which of our trig ratios do you think we're going to need here?
Tangent.
Do you guys understand why that's tangent?
Because it's the one without hypotenuse.
It's the one without the hypotenuse. I could care less how far the guy is from the tip of the rocket. So I'm going to say that the tangent of theta is equal to y over x. That's my equation. And notice it's completely devoid of information given in the problem. I'm going to leave it that way. But this is the key equation for this problem. So now what are we going to do? The derivative with respect to t. This is the important step. Related rates. Respect to t. We're doing the derivative with respect to t on both sides. Okay, so what is the derivative of tangent?
Secant squared.
Thank you very much for saying that. Secant squared theta times d theta dt. Don't forget that. You have to put that. You do the derivative, but then you have to add the d theta dt. What about on this side? What are we going to have to do? Quotient rule. Got to do the quotient rule. Just a quick reminder on the quotient rule. Remember, the quotient rule is low d high minus high d low over low low. Right? By the way, I always try to say, I'm going to just say that from here on out, because if I start trying to get you guys to say it, if someone starts saying it wrong, I'll say it wrong too.
If we already know that x is 6, we just put that in.
You could, but I'm not going to do that. I want to emphasize the quotient rule here, if that's okay with you. All right. All right, what's low?
X.
What is the derivative of high?
1.
Y prime.
Y.
Minus, what's high?
Y.
Derivative of low?
X.
X prime. Well done, sir. Guys, I'm trying to emphasize our implicit differentiation rules right now. And then what's the bottom times itself? Now, I'm going to stop here right now because I'm basically done with the calculus now. Are you guys okay so far? You know what? I should have wrote. I wrote y prime and x prime over here, and then I wrote d. Maybe I should have done it that. Is that okay if I leave it like that?
Yeah.
Sorry, that's not very good notation on my part. Okay. Anyways, so now what?
Substitute.
Okay, so what can we put in for theta?
Pi over 3.
Pi over 3. What about d theta? I'm sorry, d theta dt.
Oh, the thing. 0.9 radians per minute.
Oops, point. That's point, not negative. Are you guys with me on that? Does that make sense? Okay, what can we put in for x? Okay, so this is going to be 6. This is going to be 6. Okay, what can we put in for y?
We don't know what.
We don't know what y is, right? So we'll just put question mark there. What can I put in for y prime?
0.
I don't think so. You're telling, if you say y prime is 0, you're saying the rocket is not moving.
0.
Y prime is just y prime. This is what we're trying to find,
Oh,
isn't
no.
it?
I was thinking x prime.
That's what we're trying to find, right? What's x prime?
X prime is 0.
Yeah, guys, this distance here, is it changing at all? So this is going to be 0, which means I don't even need to know that. In fact, let me get rid of that completely. Let me make a little note here. Actually, let me erase that. And I'm going to just say, right here, I'm going to write, who cares? And the reason I say who cares is because if this is 0, it's going to be gone, right? All right, so now you got to figure out what secant of pi over 3 is.
Isn't secant squared of pi over 3?
It is, but how are you going to find secant of pi over 3?
Isn't it the
The
inverse of
opposite
tangent?
of.
It's not the inverse of tangent, it's the reciprocal of, not tangent of.
Oh,
Cosine.
cosine. So
Can you guys, now I've done all the calculus-y stuff. Can you see if you can hammer some of this out now?
It's 2.
Give everyone a chance.
My bad.
It's okay. It's okay. That's what we essentially got, right? And we just got a little hint on what secant of pi over 3 is. And what is the secant of pi over 3? 2. Then we got to square that, so that's going to make it. And guys, I'm kind of running out of room here, so I'm going to kind of go over here. So that'd be, what did we get, 4, right? 4 times 9/10 equals 6y prime over, what, 36? Okay.
We can reduce that.
We can reduce that, so anyways, so that's going to be a 2 and a 5, so that'd be what, 18 over 5 equals 6 over 36 y prime, and then what? Multiply by the reciprocal, so that's going to give us, what would that give us?
648.
648
over 30,
over 30.
which equals 86.4.
What is it?
86.4.
86.4 exactly?
Yep.
Did not quite get that. Did you divide by 4?
Oh, I didn't. It was 21.6.
Okay, there we go. That sounds better. Okay, guys, sorry. Let's go back up here. We needed to divide by 4 somewhere along the line. Let's see here.
Oh,
Dagan, where do we screw up, buddy?
when you multiplied 4 by 9, no, wait, I don't know.
Wait,
Yes.
can't you reduce 3 over 36?
To 1/6. Correct. Guys, the answer here, and the bell just rang, is 21.6, and the units here are kilometers per minute. Guys, we did it right. We just screwed up one little calculation.
Why is it kilometers? Oh,
Why is it what?
is it kilometers